VLSos here. This is a video lesson on the derivative of sine. Sine is a function. We can analyze how it changes. We're going to do that with a graph. We're going to graph sine nice and large and then analyze the change of sine right on the graph. We know that sine starts at the origin. At pi over 2 it reaches a maximum of 1. At pi, it crosses the horizontal axis. At 3 pi over 2, it reaches its minimum at -1. And at 2 pi, it completes its period. I can go back to show a little bit more than one period of sine. And if I connect these points as best I can with a sinusoidal curve, I'm reminded of the graph of sine. Let's analyze its change. Doing that is easiest at extrema. Extrema are maximums and minimums, high points and low points. If I imagined a tangent line to the sine curve right at its maximum, that tangent line would be horizontal, have a slope of 0. The rate of change of sine here is the slope of the tangent line to the curve at that point. The tangent line has a slope of 0, so I'm going to plot the derivative of sine at this location as 0. Also, at this extrema, which is a minimum, 3 pi over 2, tangent line is perfectly horizontal, so that's a slope of 0 at 3 pi over 2. In between these two zeros, sine is decreasing the entire way. Right in the middle, it has its greatest rate of decrease. If I was to draw a tangent line here on a graph that was graphed perfectly accurately, then I could reasonably observe that the slope of the tangent line was -1. The rate of change of sine at pi is -1. This is also an inflection point of sine. Sine is concave down and then switches at this location to concave up. This inflection point is its greatest rate of change. But it's going to be the same rate of change at its other inflection points. At 0, sine has an inflection point. It has it has its largest rate of change, but in this case, sine is increasing, and the tangent line would have a positive slope of +1. A few more points. At this extrema, we also have a slope of a tangent line of 0, and at this inflection point, we have a tangent line whose slope is +1. How do I connect these points? Well, let's analyze what happens between two of the points. Visualize tangent lines. At 0, sine has a tangent line whose slope is 1. And if we're to keep showing tangent lines as the point moves to pi over 2, the tangent lines go from +1 and gradually level out to 0. That's reflected in graphing the rate of change. Tangent lines have a slope of +1 and then move and gradually decrease to be 0. But the decrease isn't uniform. The change in the tangent line isn't linear or constant. The tangent lines change more slowly here, and then as we get closer to 0, the rate at which the tangent line is leveling off increases a little bit. So I would connect these points not with a straight line, but a curve to reflect that behavior. Gradual decrease in tangent, and then as we approach 0, the rate of increase or the rate of decrease increases. I can connect these any 2 points with a similar curve to capture the non-constant rate of change of slopes of tangent lines. I would connect these points like this to produce a graph of the derivative of sine, which I will put into bold. This should look familiar. This bold curve matches the sinusoidal nature of the sine curve that it came from. Observe that the bold curve looks like a sinusoidal wave that has been shifted to the right by pi over 2. It has. Analyzing a little further, the bold curve, the derivative of sine, starts at 1, has a period of 2 pi, and crosses the horizontal axis at pi over 2 and 3 pi over 2. It's cosine. The derivative of sine is cosine. If we were to give a function name like f of x and define it as sine, then the derivative f prime of x is the cosine function. What about the derivative of cosine? I could go through a similar analysis. I could show that the rate of change at cosine's extrema is going to be 0. I could plot those points. The rate of change at cosine's zeros is going to be a -1 or a +1, depending on whether I'm decreasing or increasing. And I could plot those points. I could connect them together and see that the derivative of cosine is also a sinusoidal curve. But it's not sine itself, because remember, the derivative of sine was translated or shifted to the right by pi over 2 to become cosine. Now the same thing would happen to the derivative of cosine. Shift cosine to the right by pi over 2, and we don't get back to sine. We get the reflection of sine over the horizontal axis. And a reflection is accomplished by making it negative. So the derivative of cosine is sine reflected over the horizontal axis by making it negative. Backtracking what we did before we move on, if we have a function sine, the rate of change of that function, or the derivative, is cosine. If we take the derivative again, the second derivative of the original function, we get negative sine. We could take the derivative again. It would be, in this progression, the third derivative of the original function. Or we could ask, what is the derivative of negative sine? Well, ignore the negative for a moment. We know that the derivative of sine is cosine. And then if we add the negative back in, we'll get the derivative negative cosine. Let's ask the derivative one more time. In this case, the fourth derivative of sine, which is the same thing as asking what is the derivative of negative cosine. Again, we're going to ignore the negative. We know that the derivative of cosine is negative sine. If we consider the negative now, then the derivative of negative cosine will be negative sine with another negative in front of it, which will cancel out, meaning that the derivative of negative cosine is positive sine, which is what we started with. There is a pattern here. There's 4 functions in that pattern. The derivative of sine, cosine is cosine, the negative sine, the negative cosine, back up to sine. And think about this shifting of pi over 2. If we started with the regular sine function with a period of 2 pi, and we shift it to the right by pi over 2, we get cosine. Shift it by pi over 2 again, we get negative sine. Pi over 2 again, negative cosine. And if we shift it a 4th time, which would be a total of 2 pi, then we would have shifted it a full period back into its original position of sine.